Now we're going to show you how to build your first circuit. Here are some common components that you will be using to build it. You will need a battery, a resistor, and an LED. The battery provides energy so that the charges can move through the circuit. The resistor opposes the movement of these charges, thus slowing them down and preventing your LED from burning out. The current through the LED provides the energy to the device, which transforms into light. In order to figure out how much current is flowing through your circuit, you will use a principle developed by George Ohm that states that the voltage through a conductor is equal to the current flowing through it times its resistance. Here's an example calculation using Ohm's law to find the voltage drop across a resistor. So here's our resistor, and it's given a value of 1K ohms. And the voltage across it is undefined, but we're given a current value of 5 milliamps. So if we use Ohm's law, which is V equals IR, we can just plug in our values for current and resistance to get our desired value for voltage. So here's another example of using Ohm's law to find the current through a resistor. In this case, the 9-volt source will generate a current that flows across through this 3K ohm resistor. So to be able to find this current, we need to know the voltage drop across this resistor. So since we know that this point is 9 and this point is 0, we can conclude that the voltage across this resistor is 9 volts. By using the Ohm's law, V equals IR, we can derive a similar equation for for current. So by using the fundamental Ohm's law, we can derive an equation for current, which is I equals V over R. Using this equation, we just plug in directly. 9 volts divided by 3K ohms equals our desired current value, which is 3 milliamps. So we get our desired current value, which is 3 milliamps. However, these are very simple examples. There are very few applications where only 2 electrical elements are present. To be able to solve these more complex applications, you need more advanced techniques and methods to be able to analyze them. A very important skill you will need in circuit analysis is identifying nodes. A node is a term that's often interchangeably used with point. Any point on a circuit can be defined as a node. Its technical definition is a point where 2 or more elements meet. A new node is defined at each point where the voltage is different or the current breaks off into more than one direction. So in this first example, we can see that this point right here is a node because it's a point where more than one elements meet. And this example to the right has 0 electrical elements, so the entire wire would be considered just one node. Using our understanding of nodes, we can do some pretty cool simplifications and analysis on our circuits. One example of this is in situations where we have series and parallel resistors. A series resistor are 2 or more resistors in which the current flowing through one must go into the next one. In other words, the current has no other path to take but to flow through the series resistors. So these block of resistors to the left are all in series. So this example here is a series resistance because as you can see, if a current goes through this, it has to flow through the next one. Another way to think about series resistors is that they're only connected at one node. So you can also see that these two resistors are connected at just one point. Same as this, and same as this. This last one makes it a little bit more tricky because it has three resistors. So the way you would consider this one is that resistor 1 is in series with resistor 2, and resistor 2 is in series with resistor 3. You can also see that if some current flows through here, it has to flow all the way through all three of the resistors. It has no other path to take but to flow through all the resistors. The examples on the right are not series resistors. So as you can see here, if some current was drawn through this branch of resistors, there has to be some current that flows through this one and some that flows down to the one on the bottom. In this case, this is what separates them from being a series resistors because there's multiple paths for the current to take. Same with this example. If some current is drawn to the top of this branch of resistors, there will be some that flows that way and some that flows that way. To simplify series resistance, we can find the total resistance of all the individual components by adding them all together. The expression for this is shown at the bottom. So in other words, this branch of series resistors at the top, the equivalent resistance across point A and point B is the sum of all the individual resistances. Here's an example calculation. So we have R1 and R2. We can identify this as a node, or we can also say that all the current coming in has to flow all the way across the second resistor. So we know that both of these resistors are in series, and we just indicated that the total resistance of these two is just the sum. So to find the total resistance is just R1 plus R2 equals R total, which in this case is 3K ohms. When a resistor is not considered in series, it's considered in parallel. Here's an example of some parallel components on the bottom of the slide. The two components are considered in parallel if the top and the bottoms are connected. You can also think of this as two different nodes. They're connected at two different nodes. And you can also think of it as if current flows in, it has multiple paths to flow in, so it can be considered in series. To simplify parallel resistances, we can find the total resistance by calculating the inverse of the total resistances. To simplify parallel resistances, we can find the total resistance by finding the inverse of the sum of the inverses of the individual resistances. We'll show an example of this in the next slide. So if we're given two resistances, R1 and R2, we can find the total resistance using the sum of the inverse of the resistances. So in other words, if we have 1 over R total equals 1 over R1 plus 1 over R2, this then equals R1 plus R2 over R1 times R2. But this gives you the inverse of R total. So we have to take the inverse of this, which will give us this equation here. So this is a simplified equation if you're only using 2 parallel resistances. A good way to memorize it is by thinking product over sum. The example given in this slide is R1 equals 1.5 and times R2 equals 1.5 over 1.5 plus 1.5. So this turns out to be actually half. Since R1 equals R2, R total actually equals half of R1 and R2, which is 0.75. So here's a more complicated circuit that is a good example of how to calculate series and parallel resistances combined. So here's a good example of how to calculate series and parallel resistances combined. So let's start with this branch on the bottom. What do these 2 resistances look like to you? Well, let's find out. So if a current flows through this to this branch, there will be some that break off there and some that breaks there. Also, we can say that this point is one node and this point is one node. So it's because these 2 are connected, both tops and bottoms, they're connected at 2 nodes, they're in parallel. Now let's move to the top part of this. We can clearly see that R1 and R2 are in series. So to find the equivalent resistance of R1 and R2, we just take the sum, which is R1 plus R2. Now this circuit transforms into what we have illustrated here. R1 and R2 combined, and R3 and R4 combined, and now we're left with just 2 resistors that are in series. So to find the equivalent resistance of these 2, we just add 3 plus 0.75, and we get 3.75 k ohms for our final answer.